will learn about microcontroller ports. So we will first start with what is a parallel port and how we can use these ports as serial interfaces such as UART, SPI, and I2C. Then we will learn about how we can configure these pins as an input or output and how we initialize them, how to access these registers, how to read to these input pins, or how to write data to the output ports. So here is our launchpad card that we have seen previously. So here is our microcontroller. So in this video, what we will learn is how we can configure these GPIO pins or parallel ports so that we communicate with the external world or the inputs and outputs on the card. So general purpose input-output ports are used to communicate with the external world, such as switch, and we use this switch as an input, or we can write to an LED. So LED will be our output, or we can communicate with our PC or another chip. This could be another microcontroller as well. So here is our microcontroller chip, which is called TM4C123. So in total, we have 43 IOs, and these 43 IOs can be configured as a regular IO or as an alternative functions. So if we configure you or use them as regular IO, it means they have no predefined purpose. So we can use them to read from temperature sensor or write to an output LCD or LED. So these are just two examples. Then we can use these for other purposes as well. So these GPIO pins have some capabilities, so we can configure them as an input or output. We can disable or enable them, or we can read or write to these pins. If we write to it, we can read it back, what we have written. And finally, we can use these inputs to trigger the interrupt function. So another capability of these GPIO ports, so we can also configure them as an alternative function, such as we can use it as UARTs, or we can use them as a synchronous serial interface. So this short way of writing is SSI, but in reality this is known as SPI, okay? Serial peripheral interface. Or we can use this as a I2C interface, or pulse width modulation, or quadrature encoder interface. So this is usually used for rotary encoders So you try to adjust the positions of the shaft in the motor. So this is interface is a position sensor. So this width modulation, we can also use this as digital to analog converter, or we can configure these GPIO pins as USB bus or Ethernet interface or CAN interface or ADC, or we can use these as to compare two analog signals, or we can use it as a timer where we can have periodic interrupts, input capture, or output compare. So in this lecture, we will briefly look at this UART, SPI, and I2C interfaces. So these are serial interfaces, and our microcontroller has this 8 UARTs. It has 4 SPIs and 4 I2C ports, and we have 2 pulse width modulation interfaces, and we have 1 USB, 1 Ethernet, 1 CAN, and 2 ADC with 12 bits. Each is 12 bits. Now let's look at the serial interfaces, but before that, let's try to understand the difference between parallel and serial interfaces. So assume I want to send 8 bits from B0 to B7. So I have 2 options. Actually, either I can have a parallel interface or I can have a serial interface, right? So if I try to transmit these 8 bits using my parallel interface, so I will be sending actually 8 bits in 1 clock cycle. So this is our speed is 8 bits per cycle, 1 clock cycle. But if I send it serially, I will be sending only 1 bit, 1 cycle, right? So I will be sending 1 bit per cycle. So in total, to transmit 8 bit, I will be using 8 cycles. So if I compare them in terms of speed, parallel interface is faster. Serial interface is slower, but for high frequencies, the serial interface is more suitable. So this is serial interface is very suitable for very high frequency data rates or transmission. When we look at in terms of error and noise, so parallel interface has high error and noise because these lines couples to each other. But when we look at the serial interface, we have minimum error and noise. So the parallel interface is unreliable and it requires complex cabling. But on the other hand, the serial interface is simple and straightforward. In terms of cost, the parallel implementation is of course higher, and then the serial interface is comparatively lower. So let's look at these serial interfaces that our microcontroller has. So this is our UART interface. So this might be, for example, microcontroller 1, this might be microcontroller 2, and we might be communicating between these two microcontrollers. So in UART we have these 3 lines. So this is the transmitter from the microcontroller 1, and we transmit our information, our bits, to the receiver side of the microcontroller 2. Similarly, microcontroller can transmit data to the microcontroller 1, and then what we need to do also, we need to combine or connect the ground pins of these two UART modules. So this picture is shows between two cards we are communicating. So this might be a microcontroller card. So we have this receive pin, transmit pin, and ground pin. As you see, the ground pins are connected together, and we have our transmitter connected to receiver, and then this transmitter is connected to the receiver on this side. So basically this is an adapter card. So this is called USB to UART adapter. So basically what it is doing, it is converting this UART interface to an USB interface. So the UART, basically it's a simple serial communication protocol, and it is bidirectional. So you can call it duplex. So, and it is not synchronous, so it is asynchronous. It does asynchronous transmission, so no clock required in UART. So we have only RX, TX, and ground pins. So, but in order for synchronization, it uses start and stop bits. So we will be looking at this UART protocol more detail in later classes or lectures. So basically we need to make sure the receiver understands where the package, our data package, starts. So therefore we use a start bit, and then we need to tell the receiver when to stop. So we can use 1 or 2 bits for the stopping. So we will be using some party bits for error checking. So these are our data bits actually we are trying to send. So as I said, we will be looking at this UART in more detail in the coming lectures. So we briefly review now. So let's look at this synchronous serial interface. So this is SSI, but TI calls this SSI, but more commonly this is known as SPI interface, serial peripheral interface. So in this interface, basically we have a master device and a slave device, and we have 4 signals. So this SCK means it's a serial clock. So MOSI means master out, slave in. MISO means master in, slave out, and SS means slave select. Okay, so this basically a synchronous protocol. So it is again bidirectional, it is full duplex. So it uses only 4 wires. So this is used for short distance communication, and it is developed by Motorola. So it can have one master but multiple slaves. So you can use one master and then connect one master to multiple slaves. So this is commonly used with flash memories, sensors, real-time clocks. This is called RTC. For analog to digital converters or secure digital cards. So these are some of the modules this SPI interface is used. So let's look at this waveform. As you see, I am trying to send some data from master to slave. So I am using 8 clocks. So in this 8 clock, I am sending 11001010, which is 53 in hex. This is the ASCII character S. And then in this time frame, then I am transmitting some data from the slave to the master. And if I look at, in this case, this is the master in, slave out, right? So I am sending this data to the master side from the slave side, and the ASCII character is F. So note that during this transmission, this SS slave select is a negative logic, and therefore it is low during these transmissions. So as we said, we can use this SPI in a one master multiple slave configuration. So in this case, we have our master here. So we have 3 slaves, slave 1, 2, and 3. So this serial clock is driving all of them. And then this master out serial in is also connected to these SDI pins of the slaves. So this is the slave data out, slave data out, and slave data out. So, and then to select which slave we are communicating, we will be controlling this select signals. So basically, by setting these select signals, we will be controlling different slaves. And let's look at this I2C protocol. So in this protocol, we have 2 wires actually. One is SCL, the other one is the serial data. So this is serial clock, SCL is serial clock. So we have one master, but we can connect up to 127 slaves. So we can control up to 127 slaves. So we can have also multi-master. So we can have more than one master and multi-slave. So there are different speed options. So it could have a slow speed, so you can configure it to run slowly, So this is slow, means under 100 kilobit per second. Or it can be in a fast mode. So this is 400 kilobit per second. Or you can configure it in a high speed mode, which is 3.4 megabit per second. So it uses this open drain or you can also use open collector communication standard. It means so integrated circuits, ICs with different supply voltages can be connected. So different modules with different supply voltages can be connected for communication. So these are used for some of the examples: RF tuners, video encoder decoders, audio processors, etc. So this standard is developed by Philips, and as you see, we are also using some pull-up resistors here. This is necessary because in order to control different slaves, we have to do this. And note that in this configuration, each slave has a unique address. So they will have unique address and you will be basically transmitting the bits to those unique addresses. So this is just a basic review for these interfaces. And if we have time at the end of the semester, we will be looking more detail on these interfaces. And this is a brief comparison of these serial interfaces. So their synchronization, type, the complexity, speed, number of devices that these interfaces support, and whether it is bidirectional or a single direction, and number of masters and slaves. So I will be letting you to review this table.